Hi guys, welcome to my channel and welcome to part 5 of understanding and proving the central limit theorem. So in our last class, we were discussing the axioms of a sample space. So that's where we'll start today. And then we're going to head in the direction of how we can assign probabilities to events in two different kinds of sample spaces. We'll start by looking at the discrete sample space, which is considered to be, the way to describe discrete is sort of like an integer. So if you think about the fact that if you consider only integers, there's no numbers between 1 and 2, right? So there's a space. And that's what we would consider discrete. Like there can be no partial values of a whole number. A continuous sample space is created from a sample space where the probabilities and the events are real numbers. You can think of it as real numbers. And if you've studied mathematics, you know that if you look at the real line from negative infinity to positive infinity, there are no spaces. So there's between every number, you can always find another number. And even though, you know, the line appears to be, you know, one-dimensional and it goes in direction forever and ever, even in one spot on the line, you can always go deeper and deeper and deeper into that one spot on the line. That's just the nature of real numbers. No matter how close these two real numbers are, you can always find another one between them. It's pretty amazing, actually. And that's because of something, I believe it's called the Archimedean principle, or just the idea that the real numbers are what we call a complete ordered field. Now, you don't need to know any of that for, for the central limit theorem, but it's interesting to think about it to me. So let's get started with what we need to understand the central limit theorem. And we're going to go back and review some of the axioms we discussed last time before we dive into discussing how do we assign probabilities to events in a discrete sample space versus in a continuous sample space. Okay, so those are the two main topics, right? Assigning probabilities to events in discrete sample spaces and assigning probabilities to events in continuous sample spaces. So let's go ahead and jump into this. First of all, let me go back to, see, how can I do this? Okay. So let's just flash the the theorem on the screen. You know, this has turned into quite a project for one small theorem. Now it is a kind of a small theorem, but it has no small impact, definitely, for sure. It's such a thing that may be taken for granted that it's good to stop and remember just how amazing and powerful it actually is. So let's go over here to where we stopped last time. I wonder if I could do this faster. Yeah, okay. So I'm just gonna, oh yeah, this, instead of clicking, I'll just push this. All right, so here we are. So we started by talking about a random variable, right? Because the central limit theorem says that we have a sequence of independent and identically distributed random variables, right? So we have to know what is a random variable. And we said a random variable is a function, or if you like, a mapping. So it's a function or a mapping that can assign from a sample space. So it takes a value from a sample space or an element from a sample space and assigns to it a real number value. And that real number value is the probability of that event occurring. And that event is inside of the sample space. So we have to know, you know, some basic probability, starting with what exactly is a sample space. And what is a random experiment, right? So that's where we started last time. In order to understand this random variable, or sort of like reverse engineering this whole thing. So we start with the idea of a random experiment, which is an experiment that is not only is it repeatable, but we don't know the outcome because the outcome is determined by chance. Now, we do know what the possible outcomes are, and that in general, I want to say the outcomes are finite. And we'll talk about that more later. But we have a exhaustive list of possible outcomes. And that list is called our sample space, right? So our sample space is all of the possible outcomes in this random experiment. And for each of these possible outcomes, we assign a probability, and this random variable x is how we can assign the probability. We create a mapping x from the sample space that gives a real number value for what is the probability that this event will occur. Now, the sample space has axioms, and in mathematics, the axiom, some people say it's a statement that requires no proof, which is true. But in essence, it's the bare minimum structure that we need to create something, some object or some, I had to say structure when I just said structure. It's the bare minimum structure that we need to create a space or an environment in which we can do mathematics of a certain type, right? So axioms are necessary to create the structure of a sample space. So let's see, what are the axioms here? So first of all, we said that the sample space, the probability of any event in the sample space should be non-negative. So in other words, the probability of some event A, given a sample space omega, which I didn't say here, let me just say this, I'll say it here. Given a sample space, we'll call it, can I even make omega with this? Maybe not. I'll just call it E for R, because I'm using S later. Given a sample space E with events A and B, the following must hold. So these are the axioms. That's what I'm saying. Hey, I want to make it bigger. I'm gonna move it. Oh, that's very strange. So it's overlapping. Sorry. So the probability of any event in the sample space E must be greater than or equal to 0. It's possible for it to be 0, although it's usually not happening. You can get things that are very close to 0, typically. Normalization. So normalization means that, oh, you know what? I used S for the sample space. Hold on, let me just clear everything. And we'll say, I just want to make this more correct. Given a sample space S, okay. And we'll say with events, how many ends A and B? Following axioms must hold. Okay, there we go. That's better. Okay, so normalization just means that the probability, the maximum probability essentially is 1, and that the probability of the entire sample space is 1. This means that there must be an event in the sample space that will occur. Yeah, and that essentially there cannot be an event outside of the sample space that can occur. And in other words, we are trapping the probability of some event A, so it's got a lower bound of 0 and an upper bound of 1. So the probability of any event is between 0 and 1, and this is why you get percentages. You know, you hear like, what's the probability of rain? It's about 36%. Yeah. So, but in general, you know, it could be written as a fraction or a decimal because it's between 0 and 1. Okay. The next one is called the addition rule. And we said for a pair of mutually exclusive events, so we can also call these mutually exclusive events can be referred to as disjoint, meaning that there's no intersection. There's no likelihood. Hold on, why is my handwriting so weird? So their intersection is empty. They are, in fact, what we call disjoint. So these are disjoint. And if they're disjoint, then it means that if I try to calculate P of A intersected with B, I'll get the empty set here, which is why this formula suffices. And in fact, even if they're not empty, this formula would still be, actually, because they're empty, this formula works. But if they're not empty, then we could use this formula. And this formula actually that I'm writing down now works for both cases, simply due to the fact that actually this, you know what, this should be a 0. I wrote the empty set. This should be 0. The probability of the empty set is 0. Okay. So, and so even if they're not disjoint, if A and B are not disjoint events, then I can write the probability of the union calculation like this: the probability of A plus probability of B minus their intersection. Because even if they are disjoint, this formula will still work, because the probability of A intersected with B would be the probability of the empty set, which we said last time, 0. Right? So I don't know why we need to shorten it. I always like to teach this one, but I get into the habit of convention like this. But this one is complete because it teaches you both scenarios. Okay, so let's clear this. All right, so the normality, it's going back to our normalization, which says that essentially you can think of it as there must be an event in the sample space that occurs. In normality, this is saying that every event has probability less than or equal to 1 and greater than or equal to 0. Okay, so now let's go to the few more things here. The sample space is non-empty. Okay, so this is just summarizing basically. The sample space is non-empty. Each element in the sample space must be an outcome of the random experiment. So again, like only things that are in the sample space can happen, and something in the sample space must happen. The sample space consists of all possible outcomes of the random experiment. Okay. So I think that's pretty much going to cover it as far as revision of the axioms here. And so now we can go ahead and start to talk about, let me get out of the screen, start to talk about calculating sample spaces for different types of, calculating probabilities for the different types of sample spaces that we can have. So let's see. Let me just change my screen color. And then I'll switch the screen here. Where did it go? It's because, so I'm using the Scribble ink, but it doesn't show up if you have it full screen. Maybe that's a Zoom feature, I don't know. Okay, so now I think recording. Let me just close this part. Okay, so let me just make sure the screen. Okay, so now we're good. And that should be there. Okay, great. So first of all, let's talk about discrete sample space. Now, I talked about what it means. What does discrete mean? And it means basically, like, you've probably heard of discrete data. And it's just, you know, data that cannot take on partial numbers, values. So it can't be a fractional value, it can't be a decimal. Discrete, meaning that, I guess the easiest way for me to explain it is that they're like integers, but then people might be like, well, what's an integer? So it's like one unit of something, and you can only add to the unit or take away the unit. You can never get a fraction of it or decimal. So this is what it means to be discrete. And for a discrete sample space, discrete sample space, we have typically we're going to have that. We'll call it omega. So given a sample space omega, we're going to say that let omega be finite. So we're not considering infinite elements, right? And we're going to say, and omega contains in equally likely. Now the equally likely part is kind of important elements or events, if you like. Okay, and then we'll say let A be an event in omega where A has K equally likely elements, or we could say equiprobable. Okay, so in this case, we can calculate the probability of A by simply taking the number of outcomes in A and multiplying it to 1 over the number of outcomes in the entire sample space. Okay, so this is formalizing what you know intuitively. For example, you know that the probability of a coin toss is 1 over 2 because you have heads and you have tails. You have one head, and so you multiply 1 times 1 over how many outcomes are there? 2. Yeah. And similarly, if you think about a card deck, you just want to know what's the probability of selecting any particular card. Well, how many cards are there? 52. How many of each card are there? Just 1. So the probability of selecting any particular card is 1 out of 52. Now, if you start to, you can start to change this idea by changing what sort of sample space you have and what sort of example we want to look at. So let's look at an example now. And what I'm going to do here is create a sample space for, I think this might be an impossible situation, but I don't really care. And so what I want to do is make a 3-sided dice. All right, so it's going to look like this. 2, 3. Okay, so what I'm going to do here is I'm going to let my random experiment be. So my random experiment is going to be 2 rolls of a 3-sided die. So let's say here, I'll put my first roll, I'll call it X. And here, I'll put my second roll, I'll call it Y. And so I can have 1, 2, 3 as a possible outcome here. And also 1, 2, and 3 as a possible outcome here. So suppose I want to know what is the probability that X, which is my first roll, is equal to 3. Okay, so it's simple to do. I just figure out where is the first roll equal to 3. Well, here, my first roll is 3, my second roll is 1. Here, my first roll is 3, my second roll is 2. Here, my first roll is 3, and my second roll is 3. So here is where we can get the first roll equal to 3. So according to this, by the way, there's a name for this. I write it down. So according to what we call the discrete uniform is the important word here, uniform law. So one thing we have to really emphasize while I'm remembering it is that we have equally likely elements here. So if they're not equally likely, then you can't, well, maybe it's not obvious. If they're not equally likely, then they're not going to be uniform, and we can't necessarily apply this rule. So if we have a situation where the probabilities are weighted or they're not equally likely, then we have to change our calculation. So here, what have we got? We've got x equals 3. So we have, this is our event A, right? So the k in this case would be 3 times 1 over something. And what is the total number of outcomes that we have here? We've got 3 squared, right? This is not 3 squared. So we have 3 squared, which is 1 over 9. So in the end, we get 3 over 9, which is 1/3. So the probability of rolling the 2 dice, where the first one is 3, is 1 over 3. Now, I could also talk about, yeah, okay, so let me not go too far into it, but let's just do one more thing here. And let's say I want to know, let's say I define z to be equal to the minimum of x and y. And I'll say, what's the probability that z is equal to 30? Okay, so so if I roll the dice, what's the probability that the smallest value will be 3, the smallest value of x and y, right? Okay, so let's just fill in some more of these. This is going to be 2 and 1. This is going to be 1 and 1. This is going to be 2 and 2. This is going to be 2 and 1. 3 and 2. 3 and 1. Okay, so you can see there aren't going to be. Can I give you this? So where will 3 be the minimum? Well, 3 is bigger than 1 and 2, right? So actually, the only time it could be the minimum is when it's also the maximum here. So in this case, it's just going to be 1 over 9. But I can do, what about if z equals 2? So now, when will 2 be the minimum? So let's go over here, and I wonder if I can erase that yellow. I can, but then I erase everything else too. Okay. Okay. Okay, so this is 3, 1. This is 3, 2. This is 3, 3. So where is 2 the minimum? Well, definitely not here, not here, and not here, right? So actually, starting with here, 2 is the minimum here. So basically, we're going to have to go from here and then go up and to the right. Only in these 4 squares is 2 the smaller of the dice rolls. So I'm going to get 4 times 1 over 9, which is going to give me 4 ninths. And 4 over 9, let's see if I want to write that as it's going to be repeating decimal, right? So I'll leave it like this. So this is, so the probability that the minimum dice is 2, so the smallest of the 2 dice is 2, upon rolling them is 4 over 9. Okay, so this is how you can calculate discrete probabilities. Now let me just check my time here. Okay. So, but what about if you have continuous? And by the way, this is just a really brief example using this discrete uniform law. There's more to it. If you want to know more about it, I'd be happy to make a whole series on probability. In fact, I definitely will do that at some point, because I love probability, and I also want to incorporate some of the rigor and formalism from measure theory into a probability course. So hopefully I can do that at some point, because it's a very interesting topic. And it definitely makes for a more informed data scientist, I think. So let me make sure, first of all, that I spell continuous correctly. And yeah, so now we're going to talk about a continuous sample space. So continuous data is data that basically you can think of it as data that has been measured. Yeah, data that has been measured. And one of the things about measurements is that your measurement can be as precise as you like it to be within the constraints of the sensitivity of your measuring instruments, right? So there's a really interesting story. I don't know, but I've heard it in in college. My professors mentioned this when we were talking about real analysis, talking about how if you try to measure the coastline around the UK, around the Great Britain, around the island there, British Isles, we'll say that. If you try to measure the coastline, you can find that the more precise you get, the longer the coastline gets. And so actually, the paradox is that you can end up with an infinite coastline as your measuring tools get more and more precise. And this goes back to this phenomenon of real numbers being complete ordered field. So continuous probability, continuous data, it's data that has no gaps between it. Like if you're a child and you happen to be 4'3", so what is I don't know, like let me talk about it if you're centimeters. If you happen to be 55 centimeters and then you become 67 centimeters, you can't go from 55 to 67 without going through every one of the heights in between. This is the idea of continuous data. Okay. Some data is continuous, but we treat it like discrete, like money and time. Time is continuous. However, we don't usually measure time in that way. We usually talk about time as a discrete data. If you remember back to when there were telephones that were not cell phones, you had to pay extra by the minute to call long distance. Long distance would be like from one state in the United States to another state, or even from other cities. Money is also a continuous data that is treated as if it's discrete. So continuous data, you can just think of it as something that has to be measured, okay? Now, the other issue with continuous data, well, the major issue is that if you were to, so let me just draw a graph here. So suppose I've got a graph and I will draw a little, oops. I'm going to draw a unit square here in the first quadrant. All right, so this is 1 and this is 1. And let me just make this a little bit nicer here. Okay, so now if I said to you, what's the, so here's my sample space. It's a continuous sample space. It represents this, this location in the first quadrant. Okay, so it's a continuous sample space, meaning that any point that I pick here is 2 real numbers, right? And as we mentioned before, between any 2 real numbers, well, the real numbers are like here is x. So this is its own set of real numbers here. And then y is also its own set of real numbers. And on both of these axes, there are no spaces. And so it means that we have the possibility for infinite precision. So if I ask you, what's the probability of X and Y, of any X and Y, we would have to say that the probability of the set containing X and Y would be 0. Why? Why is that? It's because you cannot get a you cannot assign a probability to infinite precision. Okay. But what I can do instead, since this is not possible, is I can define a location, right? So I can't find the probability of a single point, and that's what this is. I cannot find the probability of a single point because it's impossible. And it also has to do with, you could think about that the real numbers are not countable. So it's all tied up into these properties of real numbers. But what if I said like this? I said, okay, I can't figure out what this is, but suppose I draw some line down here, and I say, okay, we'll call this A, or we'll say, we'll say, let's say that, no, let me do like this, sorry. Okay, so basically I'm going to draw my line from here. And so now what I've got here, this is the line y equals -1/2 x plus 1/2. Is it? Yeah, should be this. Okay, so in other words, I want to know what's the probability that if I have some event over here, if I have some outcome in here, I will call this whole region, I'm going to call this an event. And now I can assign the probability to the event, and that will give me an idea of the outcomes that are in that event. And so here, this would be, the event that my points X and Y are going to be such that, let's see, I want to, make this in terms of X and Y. So it's going to be such that X plus Y is less than or equal to 1/2. And that should be correct. Yeah. Just check one thing here. So basically, I just need to change this. So this line, I wrote it down. It should be, let's call it X plus Y less than or equal to 1/2. That's the space down here, but this line is X plus Y equals 1/2. Okay, so here we can calculate this probability by using something called, let me close this up, called the uniform. So we have uniformity, we have uniform probability law. And what this does is it allows us to consider that the probability in a continuous sample space is equal to the area. Now, you still have to have all the actions of the sample space. Like, for example, my unit square, I have to have the unit square because it has to meet normalization, normality, and non-negativity, right? And that's why any PDF you see, any probability density function or probability mass function you see, the area under your probability density function will always be equivalent or equal to 1. And the sum of your probability mass function should always also be 1. So for all of the events, take the summation of all the probabilities, you should definitely get 1 because of the constraints, because of the minimum structure required to make this sample space. So for a continuous sample space, we say that the area is equal to the probability. And this has roots in, if you're interested in knowing more about this and how can we assign probabilities to areas, how can we assign volumes to like lengths in a sense, it can take up measure theory. I think, I can't remember the name of it now, but yeah, it's called The Brighter Side of Mathematics YouTube channel. Has a series on measure theory. And also, I do have to give credit to this example to MIT OpenCourseWare. Yeah, which is where I learned some of this. Outside of graduate school, I've made a lot of use of YouTube videos, and that's why one of the reasons I like to make them. But in particular, one YouTube series was so important to me, so amazing to me, was the single variable calculus by, I think it's Geraldson. And let me just make sure because I don't want to get his name wrong. MIT single variable calculus course. When I was in undergraduate school, that course really helped me. And later on, when I was teaching calculus, I would return to this course. And David Jerrison, Dr. Jerrison. And he's so insightful, and the way he goes about doing it was so interesting to me, because it really laid out to me how mathematics is working and what we're doing with mathematics. We're taking this minimum set of structures, these axioms, and we're building a whole system of mathematics that we can apply or not use, depends. But yeah, so I definitely recommend that. And I do need to, while I'm mentioning good resources, I also, when I was first taking calculus, I bought the Great Courses calculus course, and I can't remember his name now, but that was an amazing course too. It was very succinct, but also still rigorous. And the guy who made the course, who was teaching the course, I swear he was a veteran teacher, but he was definitely like a genius, and he had a really kind face. I'm trying to remember his name. I'm just going to find it right now, because since I bought the course, I still own it. And occasionally I go back and revisit them. So let me just make sure I know he's a professor in Florida. Bruce Edwards, Dr. Bruce Edwards. Definitely one of the most talented communicators of calculus I've ever seen. He just has the ability to deliver it in a way that it's still rigorous. I don't know if he does many proofs, but just can't recommend them enough. Okay, so let me go back here to revise. For discrete sample spaces, we have the discrete uniform law, meaning that we can essentially find the ratio of outcomes in the event we're interested in over outcomes in the entire sample space. For a continuous sample space, we cannot use that same strategy because it's impossible to calculate the probability of a single point. It's impossible to do because we're using real numbers that can be fractional and decimal parts of numbers, so that you can always increase the level of precision because the numbers are infinitely dense. So what we have to do then is we assign the point as an outcome to some particular event, and that event is given an area. It takes up some particular area in the sample space. And so if we want to know what's the probability of this event, then we can use something called the uniform probability law, which allows us to calculate the probability of an outcome in this event occurring by calculating the area. So let me go back to actually do the calculation here, and then I'll end it. So I'm going to take the probability of X and Y being underneath this, or equal to this line right here, X plus Y equals a half. Sorry, yeah, well, it's under that line. Yeah. And so what's the probability of something in this little red region here occurring in this sample space? And we simply find the area of that triangle. Okay, and that's it. And that's all. So the triangle has a base is 1/2. The height is 1/2. So we get the half. So what's the area of the triangle? It's a half times base times height. So we're going to get a half cubed, or an 1/8. So the probability of our event being in this little triangle is 1/8. Okay, so now we've been able to quantify the probability of an event happening that is in a continuous sample space, and we've been able to quantify the probability of an event happening that's in a discrete sample space. So now in the next video, what we need to do is figure out how do we know, the probability in this PDF? How do we know that if this is my my X, how do I calculate the probability? Well, I find the area under this curve. How do I know it's the right area? How do I know that this PDF is mapping out the say likelihoods in such a way that when I integrate it, when I find the area under this curve from here to X, this is going to give me the probability that the X is less than or equal to X, whatever this X is. Remember, we can't find the precise probability. So instead, we can figure out what's the probability of this or below it. And so I'll go into that more in detail later on. But the idea is, first of all, just remember this, that the probability in this continuous sample space equals the area under the PDF. And so we have to know, how's the PDF constructed in such a way that the areas are corresponding to the probabilities and so forth. So this is where we will start next time. Hopefully that's helpful to you. If you have any comments, suggestions, recommendations, or corrections to my understanding or to my actual work, please let me know in the comments. And feel free to please go ahead and check out those resources I mentioned. MIT OpenCourseWare, probability, Dr. Jerison, single variable calculus is very good. Bruce Edwards' course, the great courses, which is now, there was another great courses spinoff called Wondrium, which is also good. Okay, that's it, and that's all. Well, I can't find the stop recording button. Okay, that's it, and that's all.